So, yeah, I'm Arvind, uh, and yeah, I did this setting for the bronze contest. So um, I'll explain, the bronze problems. Yeah, so, so I think people generally did, quite well. Um, Probably, um, B and C were like, in some sense standard. I'll explain about them in more in depth, but this is like related to NIM. And then C is like recursion and backtracking. And then A is more like you have to come up with some observations. Um, yeah. So yeah, I'll explain the problems. So the first problem, uh, wait, let me open it. Yeah. So I think this was probably the hardest problem in the contest. So you're given a string of zeros and ones, uh, and you're given an integer k, and you're allowed to perform operations of the following any number of times. The first type is you pick a character that's equal to 0 and change it to 1. And the second operation is you pick a character that's equal to 1 and change it to 0. And you want to find the minimum number of operations so that any two ones have distance at least k apart. And it's guaranteed that the sum of the lengths of the strings in the input is bounded by something like 2 times 10 to the 5. So since it's 2 times 10 to the 5, for full credit, you'll need like a linear time solution. So yeah, so I gave some sample cases. Um, yeah, so I guess we can talk about like the first three cases. Um, yeah, so first three cases, first three cases, um, it was like it was like n is at most 10. I think more specifically, it was like, I think the constraint was like some, oh, okay. I think in the test data, sorry, I forgot to change this, but it's sum of n values up to 20. So you could do a brute force solution where this is like your input string, and then you could do like 2 to the n cases for transform string. Um, and if you do like O of 2 to the n brute force, then that should be enough for the first three test cases. And for the for to get the full test set, which is like O of n, we can do something that's greedy. So the observation is just consider the two leftmost ones that have distance less than k, and then consider the rest of the string. So everything before this has distance greater than equal to k. Um, so one observation we could make is that at least one of these has to be at least one of these has to be toggled to 0. And if you toggle this one to 0, then basically the number of interferences with the ones later is less. So it's always optimal to remove the second one if you have a pair that's less than k. Yeah. So so I'll just restate what I said. So just an observation you can make is consider like the leftmost pair of ones where the distance is less than k, and you have everything to the left is satisfied, the distance is greater than or equal to k, and then maybe here there are some pairs of ones with distance less than k. You need to change at least one of these ones to 0, and um, it interferes less with the remaining ones if you change the rightmost one to 0. So this gives a greedy strategy. Strategy. Find leftmost two ones with distance less than or equal to k, and then toggle rightmost to 0. And how you can do this is you can basically implement this in a for loop. So for I equals 1 to n, you can implement this in a for loop, and just when you see a 1, keep track of the previous one that exists. And if it has distance less than k, then change the current one to 0. So look, if si equals 1, look at previous index with sj equal 1. And if this is less than k, then that means you can toggle this one. Yeah, I'll take any questions. But yeah, any questions, ask me. Yeah, but I guess I don't know if there are other ways to do this, but if you use this kind of solution, the key idea is that you can greedily take the two ones that have distance less than k to each other, and then change the rightmost one to a 0. What does the bottom text say on the whiteboard? Yeah, so the so I'll recap. So this is the greedy strategy. So basically you can keep finding the leftmost pair of ones where the distance with each other is less than k, and then you toggle the rightmost one to a 0. Yeah, my handwriting's not the best, but yeah, that's the greedy strategy. And the reason we did this again is because everything to the left is completely fine, and we want to fix everything to the right. What's this? Yeah, everything to the left is completely fine, and we want to fix everything to the right. And if you change this one to a 0, then like these ones will interfere less with whatever's here, because basically if you change this one to a 0, then these will have longer distance to this one. If you change this one to 0 instead, then they'll have shorter distance to this one. So you always, if you ever have a pair that's less than k, you always want to delete the rightmost one. And note here, this is the leftmost pair of ones with distance less than k. How did this work if it's like, yeah, so yeah, good question. So I can walk through a concrete example. So 1, 1, 0, 1, 1, 0. So what the process is for this case is so this has distance less than 3, so I just change it to 0, and it's like 1, 0, 0, 1, 1, 0, and then I keep going, and then this has distance less than 3, and then I change this to 0, so it's 1, 0, 0, 1, 0, sorry, oops, like, yeah, 1, 0, 0. So how you like implement this is you just do a loop, and then if the current element is equal to 1, then look at the last element, which is a 1. And then if the distance is if it's less than 3, then you'll have to toggle the current one to 0. Does that make sense? Any questions? Yeah, I think Winston's comments exactly reflects this kind of solution. Cool. I guess if there's no other questions, yeah, feel free to let me know if you have questions. Otherwise, I'll go to the next problem. Okay. So the next problem. So it seems like the first problem was the hardest for most people, or it had the fewest solves. But yeah, there's this observation that two elements are less than k, then you can toggle one, and that gives you a greedy idea. Yeah. So next one is called Game on Hay Bales. So there's a game between Bessie and Mildred on N hay bales, and Bessie goes first. So in each player's turn, a player is allowed to pick any number of hay bales from 1 to 3 inclusive, and a player loses if they can't make a move. You determine who wins. Yeah, William has the correct idea. So the idea is that some of you might have heard of a game called Nim. This is kind of similar to that. Basically, the idea is that the key idea is like if you're player 2 and so if player 1, so basically player 2 can control the number of hay bales mod 4. So basically a strategy for player 2, let's just say the initial number of hay bales is 8, and then player 1 removes X, and then player 2 removes so player 1 removes X, and then X is in some number in the interval from 1 to 3, and then player 2 can basically make the sum equal to 4. So by removing 4 minus X, and then this will be 8. So basically the idea is so if the initial thing is a multiple of 4, then player 2 has the winning strategy. And then if the initial thing is like 4k plus c, where c is not divisible by 4, so basically 1, 2, or 3, then player 1 can win by removing c, so that it's 4 times k, and then player 1 basically player 1 is in this kind of state, player 2 is in this kind of state. So player 2 starts with something that's divisible by 4. So player 1 can make player 2 lose, because no matter what player 2 picks, then player 1 can always pick 4 minus X. Yeah, this is bronze. This is bronze problem 2, for those of you who are joining. Yeah. So the idea is that if the initial number of hay bales is divisible by 4, then player 2 can win, because player 2 can control the number of hay bales mod 4. And if it's not a multiple of 4, then player 1 can make it a multiple of 4. And then no matter what player 2 does, player 1 can always make it a multiple of 4. So the answer is like if n mod 4 equals 0, player 2 wins. I think they call player 2 Mildred, and then if otherwise, player 1 wins, Bessie wins. Oh, sad. Okay. Yeah, any questions? Yeah. So this is an O of 1 solution. Yeah. Okay, let's go over the last problem. Farmer John and gingerbread. So the idea is that Farmer John has an n by m. So Farmer John has an n by m size rectangular shaped gingerbread cookie and wants to cut k squares from it, where the ith square has dimensions ai by ai, with edges parallel to the sides of the rectangle. And Farmer John wants to know whether it's possible, and if it's possible, output 1, and if it's not possible, output 0. So in this case, so there's a 3 by 4 rectangle, and you want to cut 5. Yeah, you want to cut 5 rectangles, and they're all 1 by 1 rectangles. So you can do this because the area of the rectangle is 12, and you have 5 1x1 squares. So you can just place them, since 5 is less than 12. And then the second case, of a 3x4 square, and then you have 5 3x3 squares. And you can show that you can't fit it. Easy way to show it is that area of this is larger than 3 times 4. Yeah. So yeah, I'll explain the solution. Yeah, so yeah, basically the key idea is that all of these things are at most 5. So you can use brute force. So yeah, the key idea is you can use brute force. So basically you have yeah, so yeah, I guess if I draw a picture, how you should think of it is you're thinking of a place to put the first square, and then you're thinking of a place to put the second square, and then next square, next square, next square. Yeah, so I guess the way I'm the way I think of this problem is you can do this using recursive brute force. Basically, when you place your first block, in order to determine whether you can place your next block, so this is the first one that was placed, you want to determine whether next block can be placed. Basically, none of these should be occupied by the earlier block. So this is invalid, and you have to check all the possibilities for the second block, until you can find some place where you can place it. So this is something that's I think a term for this is called recursive backtracking. But basically the idea is you can recursively place them, and when you recursively place them, you can mark certain things as visited and then determine how to whether you can place the other one. So I guess when you write code for this, I think a number of people solve this, but void search, and then you'll have like your int I, which is like the index of the square you're placing, and then int x, and then int y, and then basically there's some recursive one. It's a recursive thing. You can consider like you're solving, you're calling it with argument, like you want to place index 1 first, and then yeah, and then ij for all ij, like where 1 less than ij less than equal to n, and then 1 less than equal to j less than equal to m. And what the search thing is, basically you'll have to consider like different cases. So if I greater than n, then that means you're done. And then if yeah, and then basically x and y are basically the coordinates. Like there are many ways to implement this, but x and y are places where you the top left corner. Isn't this algorithm too slow? It actually passes all the test cases, so the constraints are small enough so that it can work. Yeah, so everything is less than or equal to 5 here.
Wait, what would it would it be possible to do it with like just 5 nested loops?
Yeah, that's possible. I think you'll have to do, yeah, you can do it with 5 nested loops too. Wait, actually, can you do it? I don't know if there will be a constant factor issue. I suggest trying that, but yeah. It might work. I don't know if other people got 5 nested loops to pass.
Oh,
Yeah,
just wondering, after this, are the solutions going to be shared?
yeah, they'll be shared. Yeah, I actually wrote solutions. Wait, did it? Yeah, they'll be shared. Yeah. I think, yeah. Yeah, I'll have to figure out how to share them. I wrote them when I was writing these problems, but yeah. I haven't tested it using 5 nested loops, so I'm not sure whether or not it will pass. I encourage people to try. Yeah, the way I did it and how some other testers did it is we did it recursively. So like I is like the index of the square you're placing, and then check, and then we're letting X and Y be the top left corner. And then check if X, Y can be visited. And then if it can be visited, then for X2, Y2, like where it's like any anything for I plus 1, then just search I plus 1, X2, Y2. Yeah, and then you also have to do, yeah, so if this can be visited, then you just do like visited equals true for everything corresponding to the square, and then you search possible places to place your next square, and then you do visited equals false for everything in your current square. Yeah, let me know if you have questions. I'm going to summarize this, but yeah. Yeah, so this is, oh, what problem is this? This is bronze problem 3. Yeah, so I'm going to summarize this. Basically, you can do some kind of recursion where the state is which block you're placing, and then what's X and Y correspond to where you're placing the block. And then you can, how you do this is you check if this block can be visited, and if it can be visited, then you can assume like you have this global visited array. If it can be visited, then just mark the visited array true where the square is, and then recurse for your next block. And otherwise, yeah. And once you've done recursion for all possible locations for your next block, then you can mark visited as false. And if I is greater than n, then that means you're done and you found a solution. Yeah, and this is called recursive backtracking. And yeah, it's a standard topic for introductory competitive programming. So I highly encourage people to upsolve this if you didn't solve it, or if you haven't done much with recursive backtracking before. Yeah, any questions? Yeah, and for those who are just joining, yeah, I guess I explained the other two. Problem 1 was probably required the more tricky observation. And then problem 2 and problem 3 are more standard, but they're good to upsolve. Yeah. Any questions? Yeah, so you can't check if it's not sufficient to check if the total area is n times m. Let's consider, wait, I guess, wait. Yeah, so like if you have two squares that are like, wait, does that work? Yeah, so if your rectangle is like 2 by 4 and you have two squares that are 3 by 3, would all questions have standard in and standard out as input and output, even for silver and gold level? I think in general, yes. Um, at least to today for bronze and silver contest, they're standard in and out. Yeah. Yeah. Yeah, and yeah, I think there was yeah, during the contest, I think the scoring was a bit off for the first 40 minutes for Q3, the scoring skill. Yeah, so I updated that to 334. Recursion and brute force are are topics that people learn for bronze. Yeah. Yeah. And yeah, yeah. So I'd say like maybe a estimated cutoff or something that are these problems accurate to normal USACO level? So I think probably problem 2 was very quick to do, and I don't think there's something that quick for USACO bronze. Um, and then problem 3 was maybe on the standard side. It didn't, I don't like, I think it's like a standard topic that we learn. Um, are we doing silver right now? So I'm finishing up bronze and we'll move to silver. Um, it's a standard problem. Problem 3 is a standard kind of thing. It's still something that's pretty important and useful to upsolve. And then problem 1 probably required um or I feel problem 1 required like most observations. So I'd say the cut I estimated the cutoff score would be around wait, let me pull it up. Yeah, so cutoff scores based on like full solving 2 and 3 and getting like a few of the cases on problem 1. So my estimate would be 770. But yeah, um don't don't take like yeah, take this with a grain of salt, but that's just like my estimate because uh problem 1 was a bit more tricky. And 2 and 3 were, yeah, I guess 2, you could say 2 is unconventional. Um yeah, since it's more of like directly a math problem. Yeah. Any other questions before we move on to silver? Well, I'll pass it on to Arul.
All right. Hello everyone. So my name is Aral Kola. I am the author of the Silver Contest. So it's good to meet you all. Let me share my screen. All right. So yeah, let me just go over the contest. I think overall it went pretty well. The scores are overall, we didn't have any full solves, but overall I thought the contest went pretty well. I think the overall score distribution is also pretty nice. We had like nobody was like done super early. I think people had problems to work on throughout the entire contest, and overall everything felt like it flowed fine. So I'm happy about that. And if you can see at the scoreboard, we didn't have any full solves. But you know, there's a good variety of solves, and I actually was not expecting B to be the hardest, but I will talk about this in a sec. Yeah, so let me just get to the problems. So let's talk about problem A. So about this carnival problem, there's sort of a immediate approach which is greedy. So I'll assume you already have read the problem, by the way. I'll just actually, you know, I'll just explain it really quickly. So the idea is you have an operation on an array, which is given some elements. You can do minus p to one of them and minus 1 to the rest. And the question is, what is the minimum number of operations you need to get to 0? So the idea for this is if you're thinking about a greedy algorithm, every time we should keep on subtracting this p from the largest element of the array, right? And why would this work? Well, because it like doesn't make any sense to like sort of not subtract from the largest. Like you will always get there faster by subtracting from the largest. I mean, you can sort of go into a proof of this, but I don't want to spend too long on this. And anyway, the solution ends up taking too long because the problem is it takes a long time to update the array after each of these like operations, right? Because like even though I can figure out the largest, I have to take O of n time to, you know, subtract 1 from all the other elements of the array. So overall, this will take like O of n times max of AI time, which will actually pass subtask 2, or well, like test 2, sorry, not subtask, but like it'll pass test 2. And if you implement it correctly, where there's an edge case when p is greater than all AI, which is like AI less than p, then this is sort of like an edge case where it's you can just knock out any tower in one move, and so it's actually a lot faster. Then this should also pass test 3. Okay, so this will be greedy solution, but the problem is how do you simulate this quickly? And the answer is there's not really a good way to simulate this quickly, because every time you have to figure out what's the largest element of this multi-set in a sense, which is not really feasible. So the other way you can think about this, and this is the intended full solution, is you do binary search on the answer. So the idea of binary search on the answer, right, is let's instead check, can you knock down all blocks in T throws? This is the sort of question we need to answer, right? And then now we can just binary search the value of T, because we are asking for the largest possible value of T. So this is a monotonic function, so I can just like put the left endpoint at 1, put the right endpoint at like 10 to the 9th, because it can't take longer than that, because that's the largest element of the array, and then you find the correct value of T. So I will assume you know binary search and the answer. It's a pretty common topic in Silver, where you just need to find the largest possible answer. So you use binary search to get this value. But how do we check this? How do we perform this check? Well, let's imagine we do T throws. We know that this -1 has to happen T times to all of the blocks, right? Because every throw, we subtracted 1 from all of the blocks. And it's actually helpful to think of this as -1 on all the blocks. And then you're doing an additional minus P-1 on an extra block, right? Or an extra tower. So that means that if we do T throws, first we have to subtract T from all the towers, right? Because we have to subtract 1 from each tower every throw. So if we do T throws, we have to subtract T from all the towers. And then we have to decide, okay, which of these towers do we give this extra P-1 to? And this is where the greedy algorithm comes back in. But now the key idea is we're not having to subtract all these -1s all the time, because we already did that in this step, or we already did that here. So we don't have to subtract all these -1s. And now you can just do the greedy algorithm like the regular way, where you just keep on taking the largest element and you subtract P-1. And actually don't even need to simulate this, because you're not like having to keep on taking the largest element. What you could actually do is you could find a sum of the ceiling of AI minus T over Pi-1. Right? So what is this saying? It's saying that after I subtract AI, after I subtract T from AI, this is the number of blocks remaining, this numerator. And the denominator is the number of blocks I take away in one move. So the number of times I have to pick a certain tower is this ceiling function, right? Because if I like run out of blocks, like if I have, let's give an example. If I have 5 blocks in a tower and I can remove 2 blocks per throw, then that means I need the ceiling of 5 over 2 throws to completely remove the tower, which is 3, right? So this is the sum you need to compute. This is the minimum number of throws you need to get rid of all the towers. And so you just need to check if this is at least T, because that's what we're asking. Can we do it in T throws? So, sorry, this should be at most T. Because if we can do it in at most T throws, then this is correct. And if this is not true, then it's wrong. So this is the only check you have to do. So this is the key check function. Right, and then what you should do is you should just do binary search for L equals 1, R equals 10 to the 9th, and then do binary search to find T. Yeah, that's the whole solution. I guess the key idea, right, in this problem is this greedy solution, the thing that stops you from doing it is this sort of -1 on everything, right? That's what's stopping you. So the idea is like, how can I sort of remove that? And the idea is you can split it up into this type of operation where it's like -1, like, so this is like a uniform thing on the array. And now you realize like, okay, if I already fixed the number of times I'm doing a throw, if I already fixed T throws, then this just goes away, because now I know I have to subtract T from every element. So yeah, so this was intended to be the easiest problem on the Silver contest, and it was indeed the easiest problem. We had 14 full solves out of, I think, 50 or maybe more than 50 contestants, 51. So overall, I'm quite happy with how this went over. Let's go on to problem B. And I'll talk about, or I guess, does anyone have any questions about this before we continue? No, okay. So let's talk about problem B. I expected problem B to go a lot better. Honestly, I was quite surprised, but you know what? I actually couldn't predict this problem's difficulty, so we'll talk about it. The statement of the problem is some like flavor text about quizzes, but what you want is you want to count the number of subarrays with the sum equal to the product, right? And AR not equal to 1. Okay, so this is the sort of statement of the problem. I will actually ignore this condition for now. We'll bring it in later. Let's just focus on this because this is the sort of hard part of the problem. So the idea behind this statement, the sum equals the product, even before you sort of like do anything, I think a lot of people were trying prefix sums. And actually, you know, I'll actually talk about that first. Let's talk about the subtask, which was brute force, which was n up to, I think, 1,000, if I remember correctly. I actually saw a lot of people not even passing the subtask, which was surprising because you have to be very careful in the sense that this product here can overflow. If you're doing prefix products, right? So this is like asking what is the sum of a range. This is common prefix sums. But the problem is AI can be up to 10 to the 9th. And this range can have up to 10 to the 5 numbers. So that means that this product from AL to R can be up to the 10 to the 9 times 10 to the 5th, which is like very, like this is huge. Even if you're using like Python, your program will be very slow. And this will definitely overflow longer into 128, right? So this is, you have to be quite careful when you implement even the brute force here because especially checking for long is really careful. You have to be really careful about that. So how would you do this if you're doing the brute force? Instead of calculating all the prefix products, you should just calculate it as you go. So what I mean is like for L in 1 to N, and then what you should do is you should just keep track of the product here, right? So you say the product is 1, and then for R in L to N, or L plus 1 to N, then you should say product, actually, no, let's use product equals AFL, and then product times equals AFR, and then you should also like calculate prefix sums. Then you just check if sum equals product, right? And then you should also have a check here if it overflows. So if product is greater than, like, let's say 10 to the 18th, the product won't become bigger than 10 to the 18th because the sum won't match it. But if the product is 10 to the 18th, then you should just break out of here and avoid overflow. So this is how you should do the brute force. So actually a lot of people didn't seem to realize this, and that's why we had a lot of people not even get the brute force subtask. So this is just something to point out. But let's talk about how to solve the whole problem now. The idea of the problem is like, if we're just thinking about, okay, when does an array have the sum equal to the product, right? And the sample gave you 1, 2, 3, and 2, 2. Okay, these are sort of pretty like simple examples and they make sense, but they're kind of hiding something, right? Like, let me take some random numbers like 4 and 5, right? This is, the product is 20. How do I get the sum, which is 9, to equal the product, right? This is just some random example. Well, I can't add another like number. Even if I had 2, the product will go all the way up to 40. The sum will only go up to 11. So this is like not going to work if I add even 2. The only numbers that I could add here are 1s, because the key thing about 1 is the sum will increment, but the product will stay exactly the same. So what'll happen is I just have to have a bunch of 1s here to make the sum equal to the product. And so in general, what this means is for these subarrays, they have to have a lot of 1s, meaning that they can't have very many elements that are not 1s. So how do we solve the problem now? Well, let's actually think about what, like, how many non-1s can we have? How many non-1s can we have? Right. Well, the idea is, let's think about what is the minimum possible product of non-1s? Well, that's 2s, obviously. So if we have k non-1s, the minimum possible product is 2 to the power of k. And this value, or if we think about the minimum possible sum, is like 2k. So 2 to the power of k obviously grows very quickly with respect to 2 times k. So the idea is that since the length of the array is at most 10 to the 5th, this product should also be at most 10 to the 5th, right? And the idea that if you have a product that's way bigger than 10 to the 5th, you sort of don't have enough space to fill it with ones to get to the answer you need. So a lot of values of k work. The one I picked is k equals 20, just because it's a nice round number. Then 2 to the power of 20 is around 10 to the 6th. But you can vary this value, but some people did 30, some people did 18. But in general, just a big enough number where you're not like shorting yourself, but you're not going so big where your program is too slow. So you can sort of do some math and find the sweet spot. I just picked 20 because it's close to 10 to the 6th, which is larger than n, which is 3 times 10 to the 5th. Great. Okay, so now what we're saying is we can't have more than 20 numbers that are not 1. Well, then how do we solve the problem? Well, the idea is if we have some left endpoint, let's fix the left endpoint. What can be the right endpoint? Well, we know that first of all, this is where this extra condition of the problem comes in. The right endpoint cannot be 1, and this is kind of critical for this idea. That means that the right endpoint has to be a non-1 number, right? And we know that there are only at most 20 non-1 numbers in any good array. So like if we mark the non-1 numbers, let me just like pretend this is some array, right? And these x's are like numbers that are not ones, and then these things are like ones. Okay, right? Just some random array. We know that R can only be the first 20 values. R can only be one of 20 values. Right. So that means that I can actually just do a brute force in this sense. For each value of L, there are only 20 possible values of R. So the time complexity will only be O of 20 times N. And that's the entire solution, right? Once you fix the value of L, you know that there are only 20 possible non-1 values. And so you just have to check all of these values. There's a bit of implementation work to do here. Namely, you do need to check for overflow in the same way. You should not do prefix products and prefix sums. You should compute it as you go. And also, because the fact that there are some ones in the way, you sort of need to be a bit careful, like when you're jumping from here to here. You need to keep track of this sum because you won't sort of like keep track of it along the way. So it's a bit tricky. The implementation details are a bit tricky, and it'll be a bit hard for me to go over all of it here. But the general idea is it's actually just a brute force in the sense that once you fix the left endpoint, there are not too many choices for the right endpoint, right? And again, the idea is the intuition is you can't have too many numbers that are not 1. Another thing that I noticed a lot of people doing is like you can actually improve the regular brute force quite quickly. In fact, I know I said brute force was only 1 subtask in the problem statement, but people are getting more than 1 subtask. And in fact, my brute force that I wrote for this problem got around 116 points, which I didn't see anyone get. But you can improve this brute force just by like adding a few break statements throughout, like saying if you can make this even lower to 29 or something, this will pass pretty quickly, because if you think about it, it's kind of really hard to make tests for this problem in the sense that most tests have to be a lot of ones. And so that means that there cannot be many good subarrays, right? Most of the subarrays will be bad because like if you just have a bunch of ones and then 2, like most of these subarrays will be bad. Only like a couple of these will work. So this is around 116 points if you implement it quickly enough. But yeah, that's this problem. So I think the main point I wanted to make with this problem is like you don't have to just jump blindly into a problem just because it asks about ranges and write prefix sums and prefix products and think about that. Sometimes there's sort of ad hoc solutions, especially with math type problems, right? There are sort of ad hoc solutions. And again, the idea here is in general, very quickly, that the product on average is going to be much greater than the sum. Okay, any questions on B? Oh, okay, let's move on to C. All right, so C is a graphs problem, and more specifically, it is a problem on trees. So we have some tree, And the problem statement says we need to add one edge so that between every two vertices, there is at least two paths. So what does that mean? Well, that means that if we add this edge here, we have this, for example, as one path, or this as two paths, right? So there are at least two paths. And there are actually multiple paths. There's another path that goes like this, right? Okay, so these are sort of three possible paths from this vertex, and you can verify that for this graph, every pair of vertices satisfies the condition. So, okay, how do we solve this problem? Well, remember that a tree, by definition, right, has one path between every pair of vertices. So if we add an edge, just in general, what it will look like is we will have a cycle. We'll have sort of a big cycle and some sort of trees hanging off the end. So this is just like a very high level overview of a diagram, right? But if you imagine, because a tree has no cycles, if we add one edge, we will create a cycle and some sort of trees hanging off the edges. So this is what the graph will look like after we add one edge. Okay, now how do we check the condition, right? Well, let's imagine, for example, let's sort of imagine zooming in here on that location, right? Suppose we had like a vertex here. Sorry, suppose like this vertex is in this cycle, and we had like a tree with at least two vertices, right? Something like this. Then I claim that between these vertices A and B, there is only one path, and that's the only path, right? From A to B, or from B to A, right? We don't like, we consider the order important. So there's only one path from B to A, right? Because any other path, I have to go up. Like I have to pass A, get into the cycle, but the only way back down to A is like you have to use this twice, right? Because this thing hanging off is a tree, there's only one path up through here and down that uses this corridor twice. So the problem is we can't do that. So in general, what we need is we need a cycle and then just some nodes hanging off of it like this. Right. This is what we want our graph to look like, right? Because if we have two vertices at any point, then we get stuck. There's only one path. So this is bad. So we can't have this. So it just needs to be a single cycle with some nodes hanging off of it. So what does that mean for our original tree? Well, if we imagine removing one of these edges, right? Like let's imagine removing one of these edges. Then what we actually have is, if you imagine like unwrapping this, we just have a very long line and some nodes hanging off of this. This is what our tree should look like. So our tree, the question actually just becomes, can we make our tree a single path with a bunch of nodes hanging off of it? Okay, so this is a simpler question to tackle. We don't actually have to think about, is there a single path or two paths between a certain pair of nodes? This is a lot easier to handle. So what do we have to do now? Well, let's think about this and actually say, okay, how do we, well, first of all, actually, before we do that, how can we solve the first subtask, which is n up to 100? You can actually just brute force each pair of nodes, right? And we just need to check for each pair of nodes, does this sort of connection work out, right? So you can just actually brute force for each pair of nodes. This, you can sort of like find the path between them and then check, do all of their vertices hang off of it? So this will actually get you about half the subtasks. And I won't go into the full details of how to check, but in general, you will just run a DFS from this node and then make sure that every other node is directly adjacent to it. Okay, but how do we solve this problem for the full test? Well, again, we sort of have to bring down the number of possible like choices for our long path, right? So how do we solve this problem? The idea is we can actually choose the longest possible path. Which is known as the diameter of the tree. Okay, so the diameter is also a reasonably common algorithm about trees. That's like the one main algorithm I think you should know about trees, besides just like basic, DFS, BFS, knowing like parents and children. But diameter is quite important to know. And the idea behind this problem is, if we look at the diameter of the tree, which is the longest possible path between two nodes, then I'm going to claim that if the diameter works, then the tree works. And if it doesn't work, then the tree doesn't work. As in, like, this is a sufficient and necessary condition. Right? We need the diameter to match. And if the diameter doesn't match, the answer is no. So why is this the case? Well, let's
What do you mean by match or like work? Like, what does it mean for diameter to work?
as in, like, all the nodes are hanging off of this path, right? So I'm saying, like, if we have a tree and find the diameter, it works if all the other nodes are just like directly connected to it.
Okay.
Yeah. So I guess an example like where it wouldn't work, like if you had something like this, right? So this is the longest path, but this doesn't work because we have two nodes hanging off the tree. Okay, so how do we check this? Or, well, actually, let's prove this statement, right? I'm claiming that you can just check the diameter. Why? Well, let's pretend that this is some arbitrary thing that works, right? As in there's a path and all the nodes are hanging off of it, right? I just drew some rather random example, but let's explain why does this have to be the longest path? Well, let's say that's not the case. Let's try and find a longer path somewhere, right? Well, every path between two nodes on this graph has to look something like this. First, we have to start like somewhere down here. Then we walk along the main path and then walk down to some node over here, right? This is in general a path between two nodes on this graph. This is not any specific example, but in general, we have a path where we walk up to the main path, or sorry, yeah, we walk up to like this main long path, then walk along it and walk down. This is just like a general path. And I claim that that path is not longer than the diameter. And the reason being this section, let me actually use a different color here. This section is the same length as like the path we walked. Right, so that's already the same. So what we need is this part is, if we look at the difference, we need this and this to be longer than that and that, right? So this is only one edge, right? Because by definition, if it satisfies the problem, this cannot be longer than one edge. This is also only one edge. So that means that the only way for this to be longer is, well, these two also have to be one edge, right? Because what I'm saying is, like, if we look at this sort of diameter path versus this path, right? So the blue path cannot be longer than this sort of overlap, this green overlap. So the blue cannot be longer than the green overlap plus 2, which means that if we want the red to sort of be shorter, if we're saying that the red is not a diameter by contradiction, that means that we need the red to be the green plus 0 or 1, because it cannot be shorter than the green, because the red obviously contains the green.
Wait, by the way,
Yeah.
it's not possible to have a node connected to 4 other nodes, right? Because it's a tree. It's a binary tree, right?
The input is not necessarily binary. I don't think the prompt states this. You can have it.
Oh, okay.
Yeah. But anyways, the idea is, like, this blue path cannot be much longer than the red path. And the only thing that could happen is both of these are one edge long, right? But what that means is that this blue path has the same length as the red path. So in general, this blue path has length always less than or equal to the red path, which is the diameter, which means that we can't get a longer path, right? No matter how we try, if we have a valid tree, then there won't be another path that also works, in the sense that any other path will also be a diameter. So this means that we can just check the diameter. And how do we check, right? This is sort of a thing that we need to discuss. Let's say that we know the diameter of the tree is like some group of nodes. How do I check that all the other nodes are hanging off of it? Well, I will run a DFS from A to B, right? And at each step, well, first of all, I could figure out the direct path from A to B, or if I just root the tree at A, then I could figure out from B, I can go up the parents until I find A. So I know the exact path. I know whoever is on this exact diameter. So I need to check, are all the other nodes on it? And I mean, there's a pretty quick way to do this. The idea is, like, you sort of start from A, you go down, and let's mark all of these vertices. Right? Like, let's mark them somehow, like using a visit array. then for all the other vertices, we just need to check, am I adjacent to a marked vertex? As in, is my parent a marked vertex? Right, so you just need to check for all of these, is my parent marked? All these vertices. Because if you have some vertex down here, its parent is not marked, so we know that fails. So we just need to run the DFS, find the diameter, and mark all those vertices, and then ask for the rest of the vertices. Am I on the diameter, or is my parent on the diameter? As in, is my parent marked? Yeah, and so this will just run to no OFN because you're only doing DFSs. But the hardest part is actually figuring out most of this stuff. Yeah, I think we're just about done, but any questions about this problem? I know it was a bit confusing, but yeah.
Oh, by the way, how do we find the diameter?
Good question. All right, so this is actually like a little complicated, I guess, to explain really quickly. I'll sort of explain it. So the way you find a diameter in an arbitrary tree is you run a BFS from one vertex, any vertex. Like let's say you run the BFS and you find the farthest vertex from the root. You can pick any vertex as the root. So let's say this is the farthest vertex from the root. Now what you do is you run a BFS from this new vertex and you find the farthest vertex from this one, which will be this one, and that's the diameter. The proof is a little complicated. I mean, it's not complicated, but it's just like you need to work through it. But the idea is find any node, find the farthest node, that's one end of the diameter, and find the farthest node from this one, if that's the other end of the diameter. Intuitively, it should make sense why this is the
Wait,
farthest.
so what if there are multiple farthest ends? Then you have to do all of them, right?
Well, it actually doesn't matter because if you think about it, if we have like a diameter, right, and another diameter that's the same length would look something like this, right? Like if this is one end and we have two farthest endpoints here, right? Something like this or something like, well, we can't have something like this because it would fail. But if we have something like this, then it doesn't matter which one we pick because either way, they're sort of like this one is hanging off of this diameter or this one is hanging off of that diameter. So whichever one we pick doesn't matter. How do you find the root? It doesn't matter. The initial choice of the root doesn't matter. This is the part that's a bit, I think, hard to digest if you haven't seen diameter before, but I would say read up on it. There's definitely some good resources all over the internet for them. But yeah. Okay. So I think that's the like official end of this. We're still open for like 15 more minutes for Q&A, I think. So I'm not sure how this works.
So how hard was this mock test for silver?
Oh yeah, good question. So I was not actually expecting problem B to be so hard. I thought it was like medium hard. I thought it was about the same difficulty as 8, to be honest. So I actually put I actually like estimated the cutoff to be 800 because I thought it was quite easy, but after looking at the results, I will probably say the cutoff is around 700. Yeah, I think maybe 700 is a good cutoff. I think Prom B was just like unexpectedly difficult. So yeah, I would say maybe like do more ad hoc problems or something. It's more of like a math problem too, but you know. Cool, yeah.
Wait, so out of the 49 people, only 4 would qualify?
Yeah, I mean, this is usual, I think, for silver to gold. I think especially in your USACO, like it is a lot harder to qualify.
But like, well, last time I saw was like 15%.
Okay. I haven't seen silver to silver to gold qualification in a while. Maybe it's higher. If it's like that, I would say maybe 650, but yeah. I'll put that down here. Oh, cool. Okay. Yes, we're open for question and answers now. So if anyone has anything else. Read the answers posted. You'll probably get an email after this. I don't think they're like posted anywhere per se, but you know, they're somewhere out there. Let's see. You'll get code solution. I don't think there won't be code solutions. They'll just be like written solutions of what we explained. Gold solutions, no, this is only for the bronze and silver mocks. The gold and platinum mocks are like in a different session. The original graph had a cycle. No, so the problem statement tells you that there is exactly one path between every two nodes, which is the definition of a tree. Right. So you're given that there is exactly one path, which is equivalent to tree, which is equivalent to no cycle. Yeah. So this is useful to know like the different definitions of a tree, because USACO can give you any one of them. Right? It doesn't always have to tell you like this is a tree. Sometimes it won't tell you that. So how do you know it's the diameter again? So it doesn't have to be the diameter, but the idea is the diameter will always work in the sense that if you have a working path that like with all the nodes hanging off of it, then every other path will like work. Like every other path will be shorter than it. So yeah, there's another sort of way to think about it, which I think I saw in one solution, which is that this might be actually a bit easier to think about. It's not intended, but the idea is it's not the way I thought about it, but I saw some people write this, which is that a graph fails if it has this subgraph. And the subgraph that we're looking at is this. If this subgraph appears anywhere, then the graph will fail, otherwise it will succeed. This is a bit harder to prove, which is why I didn't want to talk about it, but it's actually it's a quite nice solution. So the reason this will fail is because any sort of cycle sort of will only connect two of these arms in a sense, or like if I have some cycle connecting these two, and the problem is these two nodes are hanging off of it, so there's only one way to get to them. Or if you have like these two nodes, like a cycle connecting those two, then there's only one way to get from here to here. And if we're cycle connecting these two is not one way. And like if you have something like this, the same thing happens. So if it has this subgraph, so that means that you actually just need to check for each vertex, sort of are there like paths of length 2 emanating from it. This is actually enough to pass the problem. It might be easier to code, but I think it's a little bit harder to see than the diameter solution. Like as in you need to prove more stuff to verify this is true. But yeah. All right, cool. Any other questions? It could be about any problem from tonight. Yeah, you needed to, I mean, you need to sort of prove this, I think, right? This is in general what you need to do with USACO Silver is that like most of the problem is not like implementing something, but in the sense you need to find the answer. And yeah, this is a very specific subject. That's why I'm saying this is actually harder to find, I think, than the diameter solution. Because, well, if you don't know the diameter, I guess maybe this is easier to find, but this is a little bit like of a random thing to think of. But you know, some people did come up with it in contest, which is quite fun. I like the solution, but it's hard. Any other questions? If n is less than the size of the subgraph, then it should be possible. Yeah, there's actually I didn't mention this. There is the silly edge case where you have this, which isn't the sample. You're welcome. But this fails because you can't add any edges. But otherwise it should work. So if you have something like this, because then you don't have the problem with this graph. The problem with this graph is you have two nodes hanging off of each side. So if you only have one on one side, like something like this, then you could connect this, and this is a valid graph because now this is only one node hanging off of the cycle. Right, yeah. So you're welcome for including this sample, which is just this node, because the problem is you can't So you just add an edge case for this. In general, actually, so you will notice like this is kind of a silly like case to put no in the sample, And the main reason I actually did this is because I feel like if I gave you a solution that's no, it would be kind of obvious. Or if I gave you in the sample a graph where it fails, the problem would be a bit too easy. Because like I said, this graph, you need to have this specific graph as a subgraph. So I can't like give you I would have to give you a pretty big graph in this sample for the answer to be no. Unless I gave you this graph, in which case it would be pretty easy to tell what the solution was. So maybe like if the solution has a pretty silly no case, it might be that they're like trying to hide something. I mean, in this sense, I was trying to hide the no case because it's actually pretty hard to make a graph that fails, right? Or not hard, but in the sense that the graph needs to be pretty big to fail. And usually the sample like setters don't want to put huge tests. It just doesn't look nice. Like we want to put simple tests that you can work on. So just some like meta problem commentary. Yeah. Is anything from anyone on C, B, or A? I will say on B, since we have like 5 minutes left. I will say on B, my brute forcer actually worked quite quickly in the sense that I did this break pretty early. Like if I got the product to be high, I would break pretty quickly. I'm guessing that's why I got so many points. But I would also say like if you have a brute force solution for this problem, like you should try and maybe make it a bit faster. Especially I think if you can see the other people in the contest and you could see like how they're, I don't know if you could see it live, but if you could see how other people were doing, then like what you could do is you could see this, like other people are getting higher scores on the brute force subtask. Because if people were just submitting the brute force subtask, they would only get like 32 points, but people are getting like 65 and 80, which would probably mean that you could improve this brute force slightly. Yeah. Okay, well, if there are no more questions, then I think we can end the meeting. I'm not sure if this works, but if anyone has anything else to say. No? Okay. Let me. Sure. Okay, well then I guess that will be it for today. So thank you all for coming. Hopefully you enjoyed the problems and learned something from them. Yeah, then like just as a reminder that XCamp like is open. We're always looking for more people to join like our winter camp and our winter quarter courses. So, feel free to join those and hopefully you had a good time with these prompts. And we will send out the recording through email, I think, with like the rest of the information, including the solutions, like the written solutions. Yeah. Okay. Well, if that's it, then thank you all for coming. And yeah. Bye, everyone.
Yes, thank you, Ariel. Thank you, Alvin. Thank you for your help and explain these problems. Also, before Alex say a couple words to the students, I'm so glad you took a long day, whole afternoon, 5 hours on this mock test. It takes some effort, but I hope you enjoy this process. Alexei USACO contest is a long journey, but it will be a fun journey. I hope all of you not only set up the goal to pass USACO, more importantly, to enjoy the journey. Alexei maybe lay down everything in your life. The journey, the process is more important than the goal. Also, I hope all of you will have a very good contest next week. If you pass, congratulations. If not, that's okay. You have more opportunities this season, also in the future. Hope you enjoy this journey. Okay, thank you all. Have a good night.
Thank you.
Thank you.